Alrighty, so a little closer to home. Milky Way, our galaxy. A little bit of interesting uh, history here. Uh, you guys are probably never watched Bullwinkle, but they had a cartoon back in the olden days called Bullwinkle, and in there, one of the little sketches they'd run was something called Fractured Fairy Tales, and it was Mr. Peabody and Sherman, I think, talking about some mythology or some fairy tale and how it telling about it. And well, I'd like to think that I'm not quite as far off as they are. There's some interesting history behind the word Milky Way here. Um, I've talked a number of times over the semester about the folks I call the early observationalists. Okay, um, they weren't exactly doing science, but they were folks with lots and lots of free time who were able to sit around and stare at stuff. We've got glacial geology from them. We got a lot of astronomy from them. And these folks who made these observations, they weren't necessarily the most well educated, the most this or the most that. They had jobs that allowed them to have free time. So picture yourself, we're going to use a sheep herder here, okay? And it's growing nighttime, and you're somewhere in Greece watching your sheep, talking with your sheep herder friends, sitting on the hill at night, looking out at the sheep, but more so looking up at the stars, eating some nice cheese, drinking some nice wine, and you look in a certain part of the sky, and there's this sort of milky white swath across the sky. And you turn to your sheep herder friend and you say, in Greek, but I don't know it all in Greek, uh, my, it looks as if the gods have spilt a glass of milk across the sky. Well, the word that they would have used for milk was galactose. Okay, and over the years, many years, we came to realize that that milky white patch up in the sky that you can sometimes see if you look the right direction at the right time um, is the looking in towards the Milky Way. Remember where I showed you we are way out in the far side of it there. Um, if you look just right, you can catch it across the sky. So these folks, even though they had absolutely zero clue they were doing it, they discovered the Milky Way, if you would. So it's sort of homage to them. Um, Galactose became Galaxy, and then we named our galaxy the Milky Way. Is again just one more sort of added tidbit there. So I always thought that was kind of neat. We already told you that the Milky Way is a spiral galaxy. What we didn't tell you is that it contains about 200 billion stars. Now, a ways back, they just rebooted a series called Cosmos. Neil deGrasse Tyson, you may or may not have seen it, but um, back when I was growing up, there was a gentleman named Carl Sagan, and he had his Cosmos show on PBS. And you guys think I'm saying some pretty strange stuff today. He was far out, man, especially in a 1970s sort of physicist, astronomer, leisure suit, turtleneck wearing, mellow kind of guy that he was. Google him, you'll see what I'm talking about. Um, he's like the Bob Ross of astronomy, all right? But he got so much teasing because he'd say there were billions and billions and billions of stars up above. And boy was he right, okay? 200 billion just in the Milky Way alone. It's about 100,000 light years across. All right. Hi. Kitty just said hi. I don't know if you guys heard her. We mentioned to you a couple times as if you view that spiral as a clock. All right. It takes that hand 200 million years to make one lap around. And in order to do that, it has us moving at about 558,000 miles per hour. Pretty dang quick. Pretty dang quick. So we don't see this view with our naked eye, but we see that cloudy patch, and what it really is just that the stars are too close together, too far away and too close together for us to make anything more out of it than a lighted up blur. But with the proper equipment, you could see something a little more like this. And you see that this looks similar to that star field that we showed you on one of our opening screens. Here's a top view. Again, just feel the need to point out this is not the real Milky Way because, well, we wouldn't be able to get a picture like this now, would we? Shows you again where the sun is, an approximate position. All right. Central bulge. It is what it's called, I guess. It's a bulge in the center. It's sort of a ball. If you remember that sideways view of this, we flip this up so we're not looking on top of it, but straight into the side. There's a ball in the center, big old beach ball. And we explained to you afterwards that quite probably they feel is a black hole. We don't really worry about the word nucleus here. So central bulge. These, by the way, are called spiral arms. Okay, there's not a vocabulary word for them here. If I were really good at editing, I would get rid of this white line here and change this word to spiral arm and have it stop, somewhere right about there. But so the Milky Way, our home. There's that central bulge for you. Obscuring dust like that too. Okay. You feeling all stretchy? Your brain getting all stretchy? I hope so. We try to go a little far, then a little close, then a little far, then a little close. So, you like story problems, right? I know I sure didn't. And I remember yelling, when am I ever going to use this? This is crazy. Da, 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 da. Turns out life is story problems. We didn't realize that when we were in 3rd grade and 4th grade and 5th grade, though. But this is the same idea, okay? Train leaves a station traveling 60 miles an hour for 3 hours. How far away is it? Right, in case you weren't paying attention, I'll say it one more time. Train leaves a station traveling 60 miles an hour for 3 hours. How far away is it? Hopefully you came up with 180 miles away, right? Okay. You got that basic idea, simple story problem. It's when they got tricky that we hated them. We could do the easy ones, though. So here's how this story problem goes. All right, size of the universe. If the universe is 12 to 15 billion years old, I told you, spoiler, that it was 13.7, I believe is where they are now. They might be up to 13.8. I think it's 13.7, though. If the universe is 12 to 15 billion years old, it has a radius of 12 to 15 billion light years. This is missing a slide. Where's the Big Bang slide? There should be a slide in here talking about the Big Bang, and there isn't. Okay. So, teaching you in this class, we're going to use the Big Bang as the accepted model for the origin of the universe. Okay, and again, I'll provide you with a few slides for these. I thought I had this PowerPoint all set up. I don't think I grabbed the wrong one, but I guess it just didn't have a handful of things that I meant to talk about. What the Big Bang tells us is that we had a very, very, very tiny point, single point. It's called a singularity, if you care. A very, very tiny point in which all of the matter in the universe was contained. And I know that sounds crazy, but because of the first law of thermodynamics, you can neither create nor destroy matter. That's how it goes. Everything that exists was in that tiny little speck. Okay, and then at some point, as you could quite imagine, it got a little jammed in there and it expanded. It expanded and it grew. And that expansion and growth is called the Big Bang. As you'll see in the slides that I'm going to add, it was so hot that the wavelengths were beyond noise. There was no Star Wars boom. Okay, and in fact, there wasn't even light for a while. Wasn't even light. I think it was about 400,000 years. They calculate that it took to cool down. Remember, everything is wavelengths, right? Sound is wavelengths, light is wavelengths. So the energy released from this expansion was so high energy that the big boom was more like the Big Bang was more like a big. Okay, but nobody could agree on how to spell that. So it just kind of expanded very, very quickly. After about 400,000 years, it started to glow. I don't know if it ever went boom, but and it kept on expanding and expanding and expanding. We feel that this happened, now to catch up to this slide, 12 to 15 billion years ago. They've more or less settled on 13.7, okay? So the idea is then, what's the fastest anything can travel? Speed of light, right, okay? So the idea is that if can't travel any faster than the speed of light, and this happened 13.7 billion years ago, or 12 to 15 billion years ago, then this universe that we just expanded should have a radius of 12 to 15 billion light years. You follow that? If a piece of matter leaves the Big Bang singularity traveling the speed of light for 12 to 15 billion years, how far away will it be? It will be 12 to 15 billion light years away. Same story problem, just different units. So, because we feel that the universe is 12 to 15 billion light years old, we expected to see a radius of 12 to 15 billion light years, giving you a diameter of 24 to 30, right? Billion light years, that is. It's big stuff. But as it turns out, it's not. They've calculated it to be much, 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 much closer to about 160 billion light years across, giving you a radius of 80 billion on either side, which is way off. Which is way off. Now, what it turns out, the first thing you might be thinking is, all right, so maybe your math's wrong. Maybe the universe is older, right? It turns out that it sort of makes sense. First of all, we know how old the universe is because of how far in it you can see. Light travels the speed of light, right? Okay. So if you can see out 13.7 billion light years in any direction, then that light has been able to travel for 13.7 billion years. If you could see 14 billion light years out, then that light has been traveling for 14 billion years. And we can't see that far, though. We could only see 13.7 billion miles out. I'm sorry, billion light years out. We could only see as far as the light has been shining. Okay, so that's how they calculate the age of the universe. They call that the observable universe. What the idea is, though, is that there is matter, there's energy, there is universe that is farther out there. And it differs from the age. And this is one place where I don't want to say they're calling in a fake rule here, but they have evidence to support this, etc., etc., etc. But what it boils down to is that they kind of had to say that there was pretty strong evidence that at one point in time, and it's a fraction of a moment, you'll see in a moment, it's a fraction of a moment that things apparently could move faster than the speed of light. I guess if mass and matter didn't really exist yet, then the um, rules of physics perhaps didn't apply to it as well. But they call this the inflation theory. Okay. Evidence suggests that the very young universe underwent accelerated expansion, and after this fraction of a second, everything slowed down to the speed of light, and that gives us um, our exaggerated distances that we're seeing. So 10 to the negative 36 seconds to 10 to the negative 32nd seconds. Like I said, when I talk fractions of a second, they're serious here. I think I have a picture. All right. So from here to here, tiny amount of time, we see this massive amount of expansion happening here. And then from then out, things slow down just, to the speed of light, of course. I've got another timeline I'm going to insert here, but I had this primarily for showing you this inflation period here. All right, changing gears a little bit here. I'll try to put some more support material in there for that expansion thing. Do try to remember, though, the actual diameter of the universe versus what just simple mathematics would show us there. Okay, the two differences in numbers there. The age of the Earth, not the age of the Earth, age of the universe is your radius, and then compared to what the actual diameter is. So let's go back, something a little simpler here to process. To Edwin Hubble. All right, we talked about Edwin Hubble. He was this amazing astronomer, very, very dedicated. And one of the things he noticed that no matter where in the universe he looked, that galaxies were moving away from us. He used, if you're familiar with Doppler effect, be it sound or light, okay, he used something called Doppler effect to realize that the galaxies around us were moving away, receding, okay? And more so, stranger, he realized that, or he measured that the farther away they were, seemingly the faster they were moving. And that part didn't make a whole lot of sense. So, first and foremost, what he came across the idea, and this one, went down fairly easy, was that the universe was expanding. Okay. Before then, and it sounds so ancient to think that, but before that, they kind of thought it was a fixed thing. Okay. Things were just kind of set in their motions, and they are what they are. But no matter where he looked, he saw that the galaxies were moving, and not just in any direction, but in a particular direction. They were expanding. But a problem with his data also showed that if in theory he could find a galaxy far enough away, well, it could be observed to be receding faster than the speed of light. Now, I know I just gave you an exception to that speed of light rule, but they don't make too many exceptions. Okay? This was a big, big, big problem. Mathematically, it could be shown to be receding faster than the speed of light, which just shouldn't happen. And that was a problem for a while. Now, here's that Doppler effect we were talking about. He noticed a red shift, okay, in the light, and it's rather involved as to how he knew this. Just suffice it to say that he knew what spectrum this light should be, but it was shifted towards red, and that indicated that it was moving away from us. If it had shifted towards the blue, it would be coming towards us. And like I said, the Doppler effect works with sound as well. If you've ever heard a police siren coming towards you and then passing you, you notice the change in the sound. Okay, the exact same thing works with light. This is one of these things where I'm just going to ask you to trust us on this one, because I don't like explaining the Doppler effect. It works great with sound. It's very easy to observe with sound. The light one's a little weirder. So what I have for you is what somebody figured out how to solve Mr. Hubble's problem. And again, I don't know the origins of this. It could have been some poor physicist sitting there one Sunday morning having a cup of coffee, reading the newspaper while some raisin bread was rising next to them. This is the raisin bread explanation for cosmic expansion theory, for the problem again of the perception that the farther away a star was from us, that the faster it would be moving. Remember that problem? All right. So this, believe it or not, explains that. It's been cycling for a couple minutes. I've purposely been killing time here. Hopefully you're watching it cycle. And what I want you to notice, we'll call this time 1 here, 5 centimeters and 10 centimeters. And we'll call this time 2, 10 centimeters and 20 centimeters. And the whole loaf of bread doubles, basically, in what we'll call 2 seconds. Okay, 1, 2, and it expands. Okay, that keeps the math simple. So in 2 seconds, we go from 5 centimeters to 10 centimeters on this side, right? And in the same 2 seconds, we go from 10 centimeters to 20 centimeters on this side. So I need you to do a little bit of math for me here. This is a change of 5 centimeters in 2 seconds, and this is a change of 10 centimeters in 2 seconds. So this one is moving at, how fast is this raisin here moving? Let's assume this raisin is fixed, by the way. Seems to not move, right? All right, so let's assume that this raisin is moving farther away from that raisin. It moves 5 centimeters in 2 seconds. That's 2.5 centimeters per second, right? Check my math, feel free. All right, on the other hand, the raisin over here moves 10 centimeters in 2 seconds. That's 5 centimeters per second. Is it not? It is. All right. So I ask you, is the raisin on the right? Where's my mouse? Is the raisin on the right moving any faster than the raisin on the left? Is the raisin on the left moving any slower than the raisin on the right? Can math lie to us? What just happened here? All right. What this shows us is this is what we would call a perceived velocity. It's just a function of the math. It's a function of doubling. This is set up to prove a point, but the point is still valid. This raisin is twice as far away as the other one was on time 1. And the expansion is twice as fast. The perceived expansion is twice as fast. The perceived velocity of expansion, I should say. It's not real. And if you really want to argue the point, the raisin's not even doing anything, right? The raisin is going along for the ride. And this is why this is even a more amazing example of this, because what scientists have come to understand is that the galaxies themselves aren't moving away from one another. Space, the empty space in between them, is what's expanding, and it's taking these galaxies along for the ride. You've heard of the fabric of space and time, right? So just imagine that all that blackness out there is something, and then all of a sudden it switches from blackness to a galaxy, and let's ignore all the minutia that's going on within that galaxy, and then just go back to blackness again as we leave the galaxy, and then there's another galaxy. There's sequins on a jumpsuit, okay? A black jumpsuit with sequins on it. And when you stretch out that material, those sequins move farther apart because the fabric is spreading them. and some sequins may move more than others, and so on and so forth, and it's all due to their original placement on that. So there wasn't, I don't think Professor Hubble ever got to hear the solution to his problem there. But somebody did figure it out that we don't have galaxies traveling faster than the speed of light. It's an error of the math, if you would. Neat stuff. Well, there's the damn Big Bang stuff. What's it doing back here? I'll move these into place, okay? I'll move these into their proper place. Explain this to you. All right. This was the piece de resistance, as they say. Pardon the horrible fake French there. This was a proof, evidence. I like the word evidence better than proof. This is evidence that the Big Bang was a real thing, that it did indeed happen. What this is, they spent, oh my goodness, years. I don't show the video anymore. There's a video I used to show that covered this in the very end. It starts with Einstein and Hubble and George Lemaitre, actually a Catholic priest who was also really into the whole Big Bang thing. Sounds like a joke, really. An astronomer, a physicist, and a priest walk into a bar, and you end up with the Big Bang theory. But so a good 4 decades later, this was mid-'80s, early '90s, we finally got up a satellite capable of mapping background cosmic radiation. Okay, and I can't get into the details of it at the moment. It's escaping my brain. But what these folks ended up mapping was the idea that there is, no matter where you look in the sky, there is just a hair above absolute zero, there's some radiation. And they feel that as the leftover fuzz from the very first event, just a little bit of reverberation still going on out there from that expansion. So I can't believe this stuff is at the end. Okay. So let's just touch base here a little bit, and then it's going to be out of order when I print it up for you. Or maybe I'll give you guys the stuff that's out of order, and I'll fix it for next semester. So in the first moment of the Big Bang, actually I got to end this timer here. 1 second. Heck, let's just keep it going for 5 more minutes. So instantly we had elementary particles. You remember elementary particles from the beginning of this semester. I've got a video I think I'm going to be showing you guys that talks a lot about this neat stuff. It's from a pretty interesting guy. I think you'll appreciate it. So in the beginning we had quarks and electrons. Remember, electrons are elementary as well. By the end of the first second, all right, all this seems like incredibly short periods of time, but by the end of the first second, we seem to have had protons and neutrons forming out of the quarks. All right, remember, protons and neutrons are not elementary particles. All right, they're made up of smaller things we call the quarks. So by the end of the first second, we had protons, neutrons, and electrons frizzling around in the early universe. I pulled this number out of the recesses of my brain somehow earlier when I told you it took about 400,000 years for light. There you go. Again, this was solely a temperature-based thing. Things had to cool down in order for the wavelengths to exist. The energy was just too high form. So after about 400,000 years, they feel the temperature cooled down enough that photons could exist. Photons are light particles. Also around that same time, they feel that we got the first elements. How do we know these are the first? Because they're the most basic. hydrogen and helium. Okay? And they are the most abundant in the universe to this day. Okay, the heavy stuff, the stuff we're made out of, the stuff the planets are made out of, it's such a small, small fraction of what's out there. It took about 200 million years for that hydrogen and helium to collect into nebula that could condense into stars. Okay, so we didn't have stars for about 200 million years after the Big Bang. And then since then, okay, remember we're at almost 14 billion years right now. So 200 million, not that big of a time period. We've gone through those stellar evolutions that I acknowledged earlier. Stars all clustered together, we call that a galaxy. Okay, just throwing that out there. We talked about stellar synthesis. We talked about the generations. Second, third, fourth generation, so on and so forth. The Milky Way came along. And that basically catches up what I had said earlier there. A lot of neat stuff. I could talk for a while about this. Much of it is tough ponderances, and things that you talk about after the bar is closed, so to speak. And you're probably wondering, oh my God, what is he going to test me about this stuff? This is so theoretical. I don't even believe half the stuff he just told me. And what? Here's the thing. This lecture, it doesn't by far represent my class when I hardly ever ask you guys to memorize numbers. With this stuff being so different, let's just say, than what we traditionally talk about, and theoretical. And I'm not making light of it. I'm not saying it's not real or anything like that, but it's not as concrete as this is made of sand, so it's a sandstone, or this is water drops in a cloud. I mean, we've talked about much more concrete stuff typically. So out of this chapter, what we're going to kind of fall back on are some of those numbers. How old is this? How big is that? How far is it to the closest star? How about the next closest star? Okay, that's that factoidal kind of stuff. There's some simple vocabulary in there too, okay? Supernova, black hole, but don't worry about the theoretical, please. Feel free to ponder it. Feel free to chat with your friends about it. Bring it up at dinner, all that awesome stuff. But I'm not going to test you on the theory, okay? If you have any questions, need more clarification on that, please feel free to ask. Take care.